Okay, so we now turn to Newton's universal law of gravitation. Okay, Newton's universal law of gravitation. And I'll tell you just a little bit about the background. As I said before, explaining Kepler's third law mathematically was one of his major goals. And again, it's probably not true that he was sitting in an orchard and an apple actually hit him on the head. It may very well have been the case that he was sitting in an orchard and an apple fell from a tree, and that's what got him thinking. But in any case, the idea was that Newton realized that the thing that caused things to fall to the ground, if you drop a rock or an apple falls from a tree or things like that, is the same force that causes the moon to go around the earth. Okay? So whatever causes apples to fall is the same that causes the moon to orbit the earth. Okay? Whatever causes the apples to fall is the same that causes the moon to orbit the earth. And this was a pretty groundbreaking idea. That means that the moon is constantly falling, which is a bit of a weird idea if you're not used to it. But through some mathematics and a lot of thinking, Newton finally arrived at an equation. And this equation, one of the most famous equations in all of the history of physics, says this: the force between two objects, okay, is equal to some constant, we'll call it big G for now, and I'll explain a little bit about what big G is here in a minute, is equal to the product of the two masses divided by the distance squared between them. Let me write that squared just a little bit better. Okay. So the force between two objects, okay, we'll break it down a little bit, is going to be dependent on the product of the masses. Okay. It's dependent on the product of the masses. And what this means is that the larger the masses, the larger the force, which is pretty reasonable. You can imagine that if the Earth were replaced by a star like the Sun, much more massive than the Earth, then the gravitational force between the Sun and that new star would be quite high, much larger than the force that the Sun puts on the Earth. Okay, so the larger the larger this product is, in other words, the larger that both planets are, or both objects, though they don't have to be planets, they can be two stars, they can be a planet and a star, they can be a planet and a dwarf star, they can be a planet and a white dwarf, they can be a star, a normal star like the Sun, and a white dwarf, or a black hole and a neutron star, any given thing. Okay, anything with mass, all right, fits into that description. So whatever this product is, the larger that product becomes, the larger the force. Now, it also makes sense that the farther away they are from each other, then the smaller that force is. So, you know, the Earth is going to experience a lot more force from the Sun than Pluto is. Pluto's much further than the Earth is, and so it doesn't feel as much force. So the farther and farther away you go, the less force you feel. And That's exactly what this equation is saying. Okay. Now, what about this G? This is called Newton's gravitational constant. And it's essentially a constant of proportionality. Okay. And it has units that make this entire equation to come out correct. Because, of course, this side's going to be in newtons. And remember that newtons is kilograms times meters per second squared. But over here we have kilograms times kilograms, so that's kilograms squared over meters squared. And so G has the units that make both sides then equal newtons. So that's what it's there for. But its value is 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. Okay, that's the value. And this is an experimental value. I should stress this. Newton knew that a constant needed to be in this equation, but he didn't know what the value needed to be. This has been done through experiment since Newton. Okay, so this is an experimental value. Now, this equation has a very peculiar thing in here in the denominator. It goes as r squared, or 1 over r squared. This is a unique feature of what are known as inverse square laws. And in fact, the two most famous field forces in all of physics, the gravitational force and the electric force, electrostatic force, both follow this exact form. Okay, so both of them are inverse square laws. So what does the inverse square law imply? It means that if you double the distance, then remember, if you get farther and farther away, the force goes down. But specifically, if you double the distance, the force gets cut by 1/2. Or I'm sorry, by 1/4. If you triple the distance, F gets cut by 1/9. And if you quadruple, F is cut by 1/16. So hopefully you can see the pattern, right? If you double the distance, you're multiplying by a factor of 2. 2 squared is 4, but it's 1 over that because the square is in the denominator. If you triple the distance, you get 9, so the force gets cut by 1/9. If you quadruple the distance, 4 squared is 16, and it goes on the bottom because it's the squared's in the denominator. So that is what the meaning of the inverse square law is. Okay, and it's one of the most important laws in all of physics and mathematics. So let's just do an example because we're now in the point where you're going to be working with scientific notation, and some of these calculations might not be terribly intuitive how to handle them. So we'll just do a quick example here. So let's say we have, we want to know the weight of a 50 kilogram person. Okay, what's the weight of a 50 kilogram person? Well, we already know how to do that one way, right? We already have the weight is equal to mg, where m is the mass of the person, and g is 10, and in truth it's 9.8, but it's okay. So if we plug in 50 kilograms, multiply by 10, we're going to get 500 newtons. the exact answer is actually, if you use 9.8, it's actually 490 newtons. Okay? So that's one way to get the weight. But we can use Newton's gravitational law to get the weight as well. Because remember, F equals ma, where m is the object that the force is acting on, but Newton's gravitational law says F is equal to big G times m1, m2 divided by r squared. And if we're standing on the surface of the Earth, then we'll let the Earth be m1, the person will be m2, and the distance between them is just going to be the radius of the Earth. Okay? So, what this means is I can rearrange this equation, and I want to know the weight of the person, so m2 is the object the force is acting on, so I can move him over to this side, and I know that this must be equal to ma. So A must be equal to everything else. Okay? And in fact, if you take the value of G that I gave you earlier, multiply it by the mass of the Earth and divide it by the Earth's radius, and I'll give you those quantities here in a second, you actually get, ta-da, 9.8 meters per second squared. Okay? So that's a very interesting phenomenon, right? This was a great triumph of Newton, that he was actually able to come up with a mathematical expression that predicted the gravitational acceleration due to the Earth. So we now can, now that we've justified the formula, we can plug it in. So the mass of the Earth is what? 5.98 times 10 to the 24th kilograms. And the radius of the Earth is 6,370 kilometers, which is 6.37 times 10 to the 6th meters. And so now that we have these two values, okay, we can go ahead and plug everything in. So F is going to be equal to 6.67 times 10 to the negative 11th newtons, newtons times meters squared over kilograms squared. And I'll just write it up here, the equation, so you can see what I'm filling in as I'm filling it in. And this is going to be multiplied by 5.98 times 10 to the 24 times 50. And this is going to be divided by 6.37 times 10 to the 6th. And that is squared. So that's a pretty big calculation. Now, you probably don't want to do this all at once in your calculator. What I would do is take 5.98 times 10 to the 24th and multiply it by 50, and then divide it by 6.37 times 10 to the 6th, and then divide it again by 6.37 times 10 to the 6th, and then multiply that result by 6.67 times 10 to the negative 11. But if you do, I promise you in your calculator, you'll get 490 newtons. Okay? So we can actually calculate the weight of a person by substituting their mass in for M2, mass of the Earth, and radius of the Earth. Okay, so you can actually calculate your weight that way, and this was a great triumph of Newton. But this formula does hold in general for any two massive objects. Again, okay, any two massive objects that are close enough to each other. Now, theoretically, of course, gravity extends forever, but there is a practical limit to how far an individual object's gravitational pull has some non-negligible value. So as long as two objects are only under the gravitational influence of each other and nothing else, then this equation perfectly describes the force that they will be attracted to each other with. Okay, so that is a very big triumph for Newton. So that is Newton's gravitational law. All right. Now in the next video we'll start chapter 6, and we will start to talk about momentum at that point. All right, we'll see you then.